Thank you, Mr. Chairman, for the kind introduction. So yeah, again, my name is Miguel Esposito Margino from Barcelona Supercomputing Center. And I'm going to, let's say, very briefly present the work that we've been doing in the last year. So what best way to start a presentation than start it in the worst way? So here, of course, like nowadays AI is everywhere, and I really wanted to show in a graphical way the fact that we all acknowledge the increase of technology in the HPC world in the last 2 decades. So I went and said, give me a graph of all the scientific publications mentioning scalability and distributed computing. This is what it gave. I mean, don't blame me for the data. It's not me. But anyway, it was just to give a graphical visualization of the trend that we are experiencing. So going to the serious stuff, this trend is also, let's say, acknowledged, improved by the development, all the technology, scientific development, that also the hardware components have seen in the HPC world. So we had NICs, network interface cards. Then we start talking about smart NICs, nowadays data processing units. We had a talk about DPA. So this is really proving the fact that there is a high technology improvement on this sense. And so there is a question which is let's say has been posed many years ago, and I guess it's still valid today. Is can we make use of this dedicated hardware to accelerate MPI communication? And we've already seen, if you were here earlier, some examples. So of course, yes, there is plenty of research that has been done on this topic. So we are not the first, and maybe we will not be the last to do. But for what we could assess is the fact that results that do not seem to actually really converge to a unified, let's say, answer. But specifically, the most blocking aspect in my opinion is that results are almost all the time not replicable, because either you are missing the hardware with which these results have been obtained, or even though you have the hardware, you don't have the software that has been built upon in order to use the hardware in the specific way. So we consider the fact that this question remains partially answered. So what is the actual benefit of hardware MPI communication offloading for large-scale applications? So we are mentioning MPI, of course. I guess everybody knows what MPI is. Message passing interface is the de facto standard when it comes to communicating between different machines. And since version 3, the MPI standard provides, let's say, the major two semantics of communicating. Blocking communication, which means, okay, you acknowledge the fact that you want to communicate something with someone, and you don't progress doing something else before the communication has been actually completed. And there is also the non-blocking communication, which by the name itself is a way to just, you acknowledge the fact that you want to communicate something or maybe receive, I don't know. And okay, when that's done, you are able to continue doing something else while the communication is being handled by someone on somebody else. And at some point, you then just go and query whether the communication has been completed, and so you can reuse whatever you want. But yeah, there is a catch here, is who is going to progress the communication. So like, for example, if you go at the post office and you deliver the packet, you know that the driver with the car is going to deliver the packet for you. But so in MPI, who is going to progress the communication? And a bit, say, small spoiler, CPUs operate sequentially. We all know that. So in this context, we try to see and think of generalized solutions, and we came up with this MOSE, which stands for MPI Offloading Simulation Engine, and it relies on a very basic idea. So we have a distributed application. So each MPI thread spawns a new thread, which it's called service thread, of course, and this thread will be the one responsible of handling everything related to MPI and communication, so networking. And yeah, we might all agree that for the spoiler that we just saw, it is essential that these two entities do not end up sharing the physical resources, because the CPU can handle only one thing at a time. And so, but yeah, how does it work? So if you would be interested in using it, how could you use this MOSE framework? Well, there are two ways to use it. So as a load time dependency, and this is specifically useful in case, for example, you don't have sources, you just have the application, just have the binaries. And so, you can still use the MOSE as a load time dependency, or if you are a developer or you're testing whatever, you can use it as a link time, but it's a compile time and link time dependency. And on top of that, in order to, let's say, to make it as seamless as possible for the user to use it, we've built like an MPI run like executable in order to effectively launch the MPI application, which supports MOSE. And so MOSE is, let's say, tries to be as configurable as possible. So we also provide the user to the way to seamlessly do it. And yes, so we said that in this scenario, it is almost crucial that the service thread and the main MPI thread do not end up sharing physical resources. So for that, MOSE also provides a way for scheduling threads or pinning threads to specific cores, so physical cores. Of course, if you want to use the EOS managed thread scheduling, you can, but you can also profit out of the ways MOSE can bind thread to specific core. And here we are just showing two ways. So interleaved, which is the preferred one, but you can also like choose a separate scheduling in case the system is supports multi-socketing. So okay, so before going to show the results, of course, it's good to explain where these results have been run. So from Barcelona Supercomputing Center, we have Mare Nostrum 5 supercomputer from since a few years, and we've only worked with the general purpose partition. So it's a double socket Intel system up to 400 gigabits per second as bandwidth, split into the two nodes, and a sustained HPL of 35 petaflops. So some of you maybe have already seen this graph earlier. So when it comes to these kind of applications, or let's say measures of HPC world, and so we have the OSU benchmarks, so Ohio State University micro benchmarks, which are the de facto standard when it comes to, let's say, a first way to assess the validity of the tools that we are developing. And they are used to measure latency, bandwidth, and it also provides a way to assess MPI communication computation overlap. And this figure specifically was just presented in the presentation before this one. And so it's the IO2LV MPI example. And this is just to report the results that some other people has recently obtained. In this case, they were actually using real hardware, so real DPUs, and 32 processes per node. But they were able to showcase that, in fact, for this case, using MPI offloading on DPUs was providing 100% overlap. So we tried to reproduce it. Of course, we couldn't reproduce it having the hardware, but yeah, logically we tried to reproduce the same example. So it's the same IL2LV benchmark from the OSU benchmarks. In this case, okay, we did not use the same specs. In our case, we used 56 processes per node. Why? Because with the MOSE framework, we are spawning 112 threads per node, which saturates fully the physical resources on each node. So we have several colors, several bars and lines here. Let me explain what these are. So we have two baseline cases. Of course, baseline, it was just the application, the test run as it was. Though the affinity, there's baseline affinity. In that case, we used an overly simplified build of the MOSE framework in which the only feature that it provides is the MPI thread pinning. So we were interested in seeing whether just pinning the thread specifically in the way MOSE is able to do just for the main MPI threads would have changed results. And then we have three MOSE configurations, so counted, normal, and no progress. So counted and normal, they were like a fully fledged MOSE implementation. The only difference is that in the counted, so the service thread is serving MPI calls and it's taking care of advancing communications. In the counted case, we implemented a counting mechanism. So the service thread was entering effectively the progress engine only when the counter threshold was hit. While in the normal, the service thread was continuously entering the progress engine unless it doesn't have to handle some MPI stuff. While under no progress configuration, we still have the service thread, so we have both main MPI thread and service thread, but we explicitly disabled the progress engine feature. So the thread was only handling MPI. And so in these two figures, and so the most important results is not that the counted and the normal were able to showcase overlaps close to 100% as well, but it's fact it showcased that if we don't have something that takes care of progressing the communications when they are asynchronous, then there's no benefit of having some external entity that takes care of MPI. But yeah, so of course, if we recall the main question of OSU are just a benchmark; they're not classifiable as a real application. So we were interested in let's say testing the framework with real applications, and in all the MPI applications, we asked, is there any real application in which we can let's say take advantage of this computation overlap? And so, okay, I also used AI in the first slide in a very bad way, but yeah, nowadays AI is the hot topic. So we looked into PyTorch. I mean, I'm sorry for the timing. It's not the best timing to show like a cake of this. I mean, don't blame me. But yeah, it really showcased the way PyTorch is built. It's very a multi-layered application. And so we looked into it, and we were so let's say, yeah, brave that we worked and we added our own custom distributed backend, which we called, of course, MPI MOSE. Why not? And so the thing that why did we look into PyTorch? Because PyTorch is well known for its built-in communication overlap capabilities via the distributed data parallel model, and which it's built upon the bucketing concept. So basically you have n replica of your model and images, and each one of them run independently up to the point where you have to update your model. And in that update, it's a bunch of IO reduce which are going on in the background. Unfortunately, very much surprisingly, this is a Python only feature. So as you could, I mean, as we saw in the previous slide, there are many layers. So the Python front end, but lower layers are written in C++. But for some reason, which I still don't understand, this feature was fully developed in Python. So even though we were, we were able to upstream our changes up to the Python front end. These were some developments that we did like in the last 3 weeks. So, but yeah, we are still suffering a synchronization issue. So we could not really use this distributed data parallel from the Python front end. So yeah, we were kind of stuck. Well, not really, because PyTorch already also provides some examples using directly the C++ front end. And if you go there, you find a distributed training which uses the NIST dataset. And say, okay, we thought, why not reproducing that functionality ourselves? So we just took the code, it's open source, we modified it, we added a way to actually, in the first place, compute add the logic to compute the overlap that it's going on, and we modify the logic in order to, let's say, very simplicity, but yeah, implement the bucketing approach as in the distributed data parallel. And so we did that, and so these are the results that we were able to obtain. So we tested that same example, training on the NIST dataset over different configuration, different nodes, using the two backends. So we first run using the built-in MPI backends, which is like it's provided by PyTorch. PyTorch developers have developed it in, and we compared it with the new one that we have had it, the MOSE MPI. And yes, overall, we were able to, let's say, provide 3 times as much overlap as the built-in MPI distributed backend. So let's go to the conclusions. Yeah, so MOSE, I mean, yeah, it doesn't want to yeah, replace anything. It was just a way to, let's say, to provide to users which might be interested to assess the potential of any kind of MPI application, whether that specific application would benefit from having actual hardware offloading capabilities. The very strong points of MOSE is that it's entirely software based, so you don't really need to have any hardware nor any specific hardware software implementation to make the hardware function properly. And it's also MPI agnostic. I didn't really mention that we basically used OpenMPI. Why? There is a reason behind, because OpenMPI, among the most used MPI implementations, is the only one that does not comply to the progress rule that MPI standard I mean defines. But MPI implementations have not agreed on a way on how to effectively interpret the progress rule. So OpenMPI does not provide any way to, let's say, to take advantage of that semantic, while, for example, MPitch has it built in. So we used OpenMPI because it doesn't have it, so we just added it using MOSE, but you can use it with any MPI implementation you want. And so we were able to show and to validate the let's say the strengths of this framework with both a synthetic benchmark, the OSU, and but also let's say close to real world application, which is the Torch model training on the NIST dataset. And both, not only they validated the approach, but they also shown say better results. So yeah, let's get back to where we started. So what is the actual benefit of hardware MPI communication offloading for large scale applications? Some of you may correctly argue, but you really didn't answer this question, right? Yes, but now we might have a way to assess this. So use MOSE and test it, and for sure we will continue testing it and maybe classify some application categories which might actually benefit from these kind of approaches. But yeah, that was a way to bridge a gap that was open earlier. So yeah, I mean, I want to thank you all the fundings that have been participating and made this research possible, and I thank you for your attention.
All right. Do we have questions from the audience?
Thank you, very interesting. So you talked about like the overlap potential of performance. Do you have any idea how does that translate to like application performance?
Yeah, that's yeah, very nice question. And but of course the answer I would say it's very application specific, because I mean how can you actually I don't know, you should be able to have an idea of the compute intensity of the application, which you cannot really have it if you don't start testing it. So, I mean, for the, of course, the OSU benchmarks, if you let me go back, I mean, in that case, but of course, that's a benchmark, but we had a 2x speedup. It's twice as fast, but it's because, of course, it's just doing that. So if you then the application has all the logic independent from the communication itself, it's really application dependent. That's why, I mean, that's why we didn't really answer the question, but we are trying to propose a way to answer the question, which is independent from any hardware vendor specific thing. So it's only, I mean, I don't know, you have a very big MPI application and you're thinking to buy an hardware, just test it. You see if it might be worth it. If it is worth it, then you go and do the real thing. So, but I mean, I cannot answer really like on a general, it's very application specific. So in this case, it was twice as fast. And the PyTorch was, we didn't really reported it, but yeah, it was kind of a 10%, something like that. Yeah. But yet it's a toy model training yet. I mean, medium size, let's say, medium size. But so yeah, but the potential is there. It was just that something to actually assess was missing.
Other questions? If not, then I have one.
Yes.
So if I understood it correctly, you essentially have another thread that pushes the progress engine.
Yeah.
And I wonder, like, it's all about in the end getting an idea of how the optimization potential is if you offload something to hardware, right?
Exactly.
So what would be the actual thing that would be offloaded to hardware? Like right now you're pushing like the progress engine, but what should be done in hardware then as an optimization later on? I know there's tag matching already in sophisticated network hardware, but what else can you think of is going to be offloaded to hardware then in the end?
That's a nice question. I'm not really a hardware guy for the moment yet, but so I'm not really able to answer this question. It's, I mean, it would be I mean, I would say it would be interesting to let's say to discover what can be done on that aspect, whether like doing something else can improve performances or not. I would say at the end of the day, offloading to DPU, so it's networking, so it's just about moving data across the network. But I mean, why not discovering that if you just add some pieces to that picture, you might even get better
because
performance.
there needs to be some interaction between the device that you offload communication to or parts of what MPI is internally doing to the host, and then you have like a communication bottleneck between the offloading device that is something doing within your MPI implementation Okay, that would be interesting to see in the future.
Sure. I mean, I think it's this point is still unclear today. So
yeah, and I understand the work is like giving it a potential.
Exactly, and then you go and effectively inspect having the hardware on.
Yeah, but it could have been that you already have some idea where the journey is going to.
Yeah, sure.
All right. Another question. Yes.
Great talk. Thank you. So previously, one of your colleagues also presented another infrastructure that is actually taking and offloading some of the work as a future vision. What is your looking ahead? How would all this environment of the software infrastructure that can actually offload or have something similar to yours will affect this next generation applications? And
yeah, yes, it's a great question because I think this new hardware and all these new, let's say, developments that are being done due to the hardware advancements are showcasing that the way most, I mean, I'm not speaking for the entirety, but most of the application when are based on MPI are using a semantics which is not aligned with the developments in the hardware sense. So it might be that in order to effectively use this hardware as much as we can, we might reconsider the way we are using these paradigms in the application. So changing the logic in order to make space, which is not there yet, for having this communication computational overlaps. So it might be, yeah.
We
Thank
still
you.
have time for another question. Well, if there's no other question, then we thank our speaker again.